All right, welcome everybody. Today we are going to talk about Calc Lesson number 17, and this is day 2 of the chain rule. We're mostly going to focus on harder versions of the chain rule problems and more specifically on trig. Before we get started, let's go ahead and just review what the chain rule is. And notice that there are two different versions of the chain rule, and there are pros and cons to both. So the first one is using F and G, and thinking of it more in terms of a composition. So here's what it says. If you have both F and G, which are both differentiable, which again, they always will be, that's just a qualifier that we have to kind of point out. So what it says here in the first version is if you are taking the derivative of a composition, you're going to start first by taking the derivative of the outside function, which would be f, and then take the derivative of the inside function, which would be g. Then the second kind of notation is if you're taking the derivative of something with y's and x's, you're going to call that dy dx. You're first going to take the derivative of y in terms of u, and then you're going to take the derivative of u in terms of x. So there are pros and cons to both of these versions, and we're going to talk about them more in 2.4 and then also in 2.5. Just in case you're wondering why there are two versions, there are two men who try to take credit for the creation of calculus. One of them you're probably familiar with is Sir Isaac Newton. This first notation is his. He's actually thought to have discovered calculus during the plague in the 1300s, so really makes you kind of think about what you were up to during the coronavirus plague this past spring. The second notation here comes from a German mathematician, Leibniz, and he was working on calculus separately. And so both of their contributions are considered to be correct, but they're just kind of different. So again, just in case you wanted to know that fun fact, and just in case you were wondering where the two different kinds of notation came from. So let's go ahead and just review a couple of easier problems before we get on to the trig stuff. But I also want to point out here that not only are we going to review some problems, I'm also going to show you some new notation. This notation you have to use once we get to 2.5. For now, it is still considered to be optional. So I'm going to do about half the problems today using it. And then when you get to the homework, I'm going to kind of leave that up to you, whether or not you want to employ it, keeping in mind that you are going to have to use it when you get to 2.5. So it's really kind of up to you whether you want to start doing it sooner rather than later. So here's our first problem of the day. And again, you're trying to use the chain rule to take the derivative. So as we take a look here, doesn't look like there's any rewriting that we have to do. So we're going to go ahead and jump in. We're going to take the derivative of y, which we're going to use Leibniz notation. So we're going to say dy dx is equal to, according to the chain rule, we're going to bring down the 3. Then we're going to take the entire quantity, x squared plus 4x, to the 1 less power, which would be squared. And then here's where the new notation is, and it's really kind of just a reminder. You now have to take the derivative of the inside. What you're actually doing is you're taking the derivative in terms of x of the inside, which is x squared plus 4. So really, you're just writing out first what it is you're taking the derivative in terms of what variable before you actually do it. So then once you've written out what it is you're going to do, you go ahead and do it. So 3 times x squared plus 4x squared. If you take the derivative of x squared plus 4x in terms of x, that's 2x plus 4. Then from here, in terms of anything that you can multiply, you actually could leave that as your final answer. You could also just try to combine a little bit by taking this 3 and multiplying it through to get 6x plus 12 times x squared plus 4x squared. And again, the truth is that either of these versions would be completely correct. And again, just like earlier in the chapter, if you're working on a problem, you can always ask your teacher, did I go far enough? Do I have to go farther? On a test or quiz, it would say factor, multiply, whatever it is we were looking for. So nothing really new about this problem, but again, just to focus on the notation. So let me show you another one with that new notation. So let's say you had 2 over t plus 5 squared. So something to notice here is that you have a t variable instead of a y. So that would change your notation just a little bit. From here, I am going to do a rewrite step. I'm actually going to square the numerator and square the denominator. So if I square the numerator, I get a 4. If I square the denominator, I get a t plus 5 squared. I'm then going to rewrite this as 4 times t plus 5 to the negative 2. Again, all of that is still y equals because I haven't actually taken any derivatives. Then in this problem, I'm going to take dy dt because I'm taking the derivative of y in terms of t. You have to always leave the variables, correct? I'm going to bring down this negative 2 times 4 gives me negative 8. Then I'm going to take the entire quantity, t plus 5, to the 1 less power, which would be negative 3. And then again, using the new notation, what is it that I have to do next? I have to take d dt, which means the derivative in terms of t, of the inside, which in this case is t plus 5. Luckily for us, the derivative of the inside, the derivative of t to the first, that's like taking the derivative of x, which would just be 1, and the derivative of a constant is, of course, 0. So for my final answer here, there's nothing really to clean up other than to make a positive exponent. So I'm going to leave my negative 8 on the top and then move my t plus 5 to the positive 3 into the denominator. So first, just to kind of get your mind working, again, reminding you of what the chain rule is and then showing you that new notation. So I'm going to use that new notation, again, for about half the problems going forward. And then for now, it's up to you whether you want to employ it or not. The majority of today's lesson has to do with trig, and if we're taking the derivatives using trig, we have to remember what the 6 trig derivatives are. They're the same as they were earlier in the chapter. They're still on that formula sheet. You should still have them written down, but again, I would strongly recommend that you always have those formulas handy, and we're going to go ahead and be using them. So find the derivative of y equals the sine of 2x. So this is the first time that you've been asked to take a derivative with the chain rule, with a trig function. The thing you want to focus on when you do these problems is you want to look for the big picture. Is this a sine function or is this a 2x function? Whichever is the big picture function, that's the outside function, and you would take that derivative first. Hopefully you would agree that this is a sine function. So I'm going to start by taking the derivative of the sine. So dy dx equals the derivative of the sine of something is the positive cosine of the same something, and then you have to take the derivative d dx of the inside, which would be 2x. Then if you go ahead and take the derivative of 2x, it's just 2, which means your final answer, dy dx, is equal to 2 cosine 2x. And again, that's this new notation here. It's always going to be a d in the numerator and then d, whatever the variable is, in the denominator. And for now, it's just a reminder, helping you to remember what's the inside function, what's the outside function, and then how many times you have to actually use the chain rule in a row, because sometimes it's not just 2. Here, we're taking the derivative of the cosine of 1 minus x. So again, you want to ask yourself, big picture, is this a cosine function or is this a 1 minus x function? And hopefully you would agree that this is a cosine function. So dy dx, the derivative of the cosine of something is the negative sine of the same something. And then you have to take d dx of the inside, which is 1 minus x. So negative sine of 1 minus x, the derivative of 1 minus x would be just negative 1, which means your final answer, dy dx, would be the positive sine of 1 minus x. And if you're thinking to yourself, yeah, these aren't really too bad, well, that's true. They're not, as long as you're methodical and follow all the steps, just like always. All right, so y equals the tangent of 3x. So now we're kind of cooking. I think we could kind of realize that this is definitely a tangent function. So these are kind of also to remind you about your trig derivatives. So the derivative of the tangent of something is the secant squared of the same something. Instead of using the new notation, the derivative of the inside would just be 3. So maybe I don't need to show that work, which means my final answer is going to be 3 secant squared of 3x. Again, I think you'll be able to see by the end of the lesson when it would be a good idea to use the notation versus when you don't really need it for now. But again, I'll let you wait till the end to decide. All right, the next three problems, notice that they all look fairly similar, but they're actually not. They're going to get quite different answers. So really the focus of these next three problems is using parentheses when there are parentheses given versus times where you think that you can put them in. You have to be very careful. You're only allowed to put them in exactly where they're allowed. So first, just take a look here at the three different versions, and then let's go ahead and get to it. So in the first version, the cosine of 3x squared, if you wanted to put parentheses somewhere, the only place you could put them would be here around the entire 3x squared. So if you did that and we went to take our derivative, dy dx, you would be taking the derivative of the cosine of something. So the derivative of the cosine of something is the negative sine of the same something. Take the derivative of the inside, which would be 3x squared, so the derivative would be 6x, which would give you a final answer of negative 6x times the sine of 3x squared. And again, whether you put that 3x squared in parentheses or not, you could put these, but that's the only place that you could put them. Compare that to the cosine of 3 times x squared. So here's the thing about the cosine of 3. I know it seems a little funny, but the cosine of 3 is a constant. If you were to plug that in your calculator, it would be a decimal. So this problem is really no different than taking the derivative of just 3x squared. It's not actually the chain rule. It's not actually the product rule. It's really just equivalent to taking the derivative of 3 times x squared. So how would you take this derivative if you know that the cosine of 3 is a constant? Well, you would start by bringing down the 2 times the constant, which would be the cosine of 3. Then you would take the x to the 1 less power. 2 times the cosine of 3. Again, this is really a constant, 2 times the cosine of 3, so you could put parentheses around it if you want, and it looks like kind of a funky answer, but it is the answer nonetheless. 2 cosine of 3 is just a constant times x to the first. So the chain rule, remember, is great. We love it, but you're not going to use it all the time. I mean, you're going to use it most of the time, but just make sure that you don't use it when it's not appropriate. And then finally, the cosine of 3x, the quantity squared. My advice, if you see something like this to a power of 2 only, you would go ahead and actually square whatever's on the inside. So that would give you the cosine of 9x squared, which you would then be allowed to put in parentheses if you wanted to. As long as this is only a monomial, meaning there's no addition or subtraction, whatever this exponent is, you should just cube it or square it or do whatever the case may be. If it was a binomial in here, squaring it would probably be good. Anything more, maybe not. But I'm going to go ahead and square the 3x to get the cosine of 9x squared. So now when I go to take the derivative of the cosine of something is the negative sine of the same something, times the derivative of the inside, which would be 18x, giving me a final answer of negative 18x times the sine of 9x squared. And if you were to go back and compare the three answers to the previous three problems, I think you would agree that they are, in fact, quite different. So order matters, and parentheses really matter. So if you're going to add them in yourself, be extra careful. How about the cosine squared of x? Before you even think about doing this problem, you have to rewrite it as the cosine of x squared. If you don't, you're kind of dead in the water. Here's where the big picture question really starts becoming important. The cosine of x squared. This is no longer a big picture cosine problem, but this is actually a big picture, a squared problem. So at its core, this is an x squared problem, which means the first thing you're going to do is you're going to use the power rule. So instead of the trig function being the outside, it's now going to be the inside. So again, big picture lets you know what you have to take the derivative of first. So when I go to take dy dx, I'm going to use the power rule, which means bring down the 2, take whatever the function is to the 1 less power, which would be the cosine of x only to the first. Then take the derivative of the inside, which in this case, you're taking the derivative of the cosine function. That would be the inside. That would be 2 times the cosine of x times the negative sine of x. And to clean that up, you're just going to go ahead and put the negative out front. It doesn't matter who goes first, the cosine or the sine. They're both considered to be equally important. Kind of something similar here, the cosine of x, the square root of that. So the first thing you're going to do is you're going to rewrite this as the cosine of x, the whole thing, to the 1/2 power. This is similar to the previous problem that at the end of the day, this is a power rule problem because you're taking something to the 1/2 power. So the first thing you're going to do when you take the derivative is you're going to use the power rule. So you're going to bring down the 1/2. You're going to take the entire quantity to the 1 less power. So 1 less than 1/2 is -1/2. Then you're going to do the derivative of the inside, which would be negative sine. And then for your final answer, we know that there's a 2 in the bottom because of the 1/2. We're going to leave the negative sine of x in the numerator, and you're going to bring the cosine of x to the denominator, and you can either write it as the square root of the cosine or the cosine to the 1/2. It doesn't matter which one, and also it's perfectly fine that you have a square root in the denominator. That really is not an issue in these kinds of problems. All right, so if you thought that was fun, let's take a look here. The sine of 2x times the cosine of 3x. If you're trying to identify what is the big picture here, you're actually being asked to find the derivative of something times something, which means this is at its core a product rule problem, which you can see I brought the product rule back here to help us. So it's the product rule plus the chain rule, because as you take your derivatives, you have to take the derivative of the inside. So this is super fun. You're going to take dy dx, and let's see, how advanced we are at this point, whether we have to write our ff prime and gg prime. Again, can keep doing that as long as it's helpful, and if you don't need it, then great. So according to the product rule, you're going to do the first times the derivative of the second. So the derivative of the cosine of 3x is the negative sine of 3x. Then you have to take the derivative of the inside, which would be 3, plus the second, which is the cosine of 3x, times the derivative of the first. So the derivative of the sine of 2x is the cosine of 2x. Then you'd have to take the derivative of the inside, which would be 2. In terms of how you're going to write this, we're going to put the positive thing first. So I'm going to take this entire quantity, and I'm going to say 2 cosine 2x cosine 3x minus 3 sine 2x sine of 3x. And in terms of simplifying, that is really the most that I can do here. Again, it doesn't matter which goes first, cosine 2x or cosine 3x. They're both considered to be equally important. You either go from the smaller to the larger or from the larger to the smaller. So from here, just be careful. So a little note here, if you were being asked to multiply the sine of x times the sine of 2x, you can't multiply them because they're different. If you were being asked to multiply the sine of 2x times the sine of 2x, that would equal sine squared of 2x. So you're allowed to multiply the signs as long as they're of the same quantity. And if they're not of the same quantity, then you would just leave them separate. So our final 2 problems of the day, this is as hard as it's going to get, at least for today. We're going to bring back that notation from the beginning of the lesson because you're actually going to have to do the chain rule 3 times. And again, the first step for a lot of these problems, as always, is the rewrite step. So if you're doing the sine cubed of 4t, the first thing you're going to do is you're going to rewrite this as the sine of 4t cubed. That means that at its heart, this is a power rule problem, which that means that's the first thing that I'm going to take the derivative of. Notice that because we're back to f of, we have to go back to our f prime notation. So I'm going to bring down the 3. I'm going to take the entire quantity to the 1 less power, and then I'm going to have to take the derivative in terms of t of the first inside, which in this case is the sine of 4t. So 3 sine of 4t, the whole thing squared. When you now take the derivative of the sine of something, that is equal to the cosine of the same something, and now you have to take the derivative of the new inside, which in this case would be 4t. It's the first time we've ever had a case where you had a new inside and then you had another new inside. So in the final round here, 3 times the sine of 4t squared times the cosine of 4t. The derivative of 4t is 4. And in terms of how you should write this final answer, 3 times 4 is 12. Then you have the sine of 4t squared, which most times you'll see the book write it as sine squared of 4t times the cosine of 4t, and that would be your answer. Again, it doesn't really matter what goes first, the sine or the cosine, and it doesn't matter whether you left the sine like this or whether you wrote it as a squared. They're both considered to be equally correct. And then our final problem of the day, kind of just like the last one, you have to do a threefer, and let's just focus on that notation. So the first thing you're going to do again for f of t is you're going to rewrite this as 5 times the cosine of 3t, the whole thing squared. The fact that you're writing it as something squared, again, at its core, this is a power rule problem, which means that's what you have to take the derivative of first. So bring down the 2 times 5 is 10. You're going to take the entire inside to the 1 less power, and then you have to take the derivative of the first inside, which is the cosine of 3t. So 10 times the cosine of 3t. The derivative of the cosine of something is the negative sine of the same something, and then you have to take the derivative of the new inside. So 10 times the cosine of 3t times the negative sine of 3t times 3, which is going to ultimately give you a final answer. Find the 10, the negative, and the 3 to give you negative 30 cosine of 3t times the sine of 3t. So here is homework number 17. This is still in section 2.4. Again, all of these problems require the chain rule in some capacity. Whether you use that new notation or not, again, we'll leave it up to you to decide for now. Pay attention to the variables that are being used and pay attention to your notation. Most importantly, you're looking for big picture, so that takes you tells you what to take the derivative of first.